Hello and welcome to Toddcast number 14. It's kind of, if you will, part three of resonance and the impact on resonance. Anyway, as I'm making these, I'm going through, this is number 14, what ultimately will be, if it stays to form, a 63 set of Toddcasts that will cover first semester organic chemistry, and then I'll start into the next approximately 50 that will cover second semester organic chemistry. So it's a project in the works. Hopefully they've proven useful. Actually noticed I started getting a following in uh, YouTube, and I'm assuming it's actually people not enrolled in a course I'm teaching, um, be it at Pepperdine where I'm at right now, or any school that I used to teach at, or any MCAT course I used to own. So it's kind of interesting. So I'm going to try to keep that in mind moving forward. For those of you who've never heard of me before, my name is Todd Bennett, old person who's taught a lot of organic chemistry over the years, and just wanted to put out kind of a collection of what I've done mostly over the past 3 years, but it actually started about 35, 40 years ago and have just been sort of snowballing and building a bunch of information, a bunch of lectures. So hopefully they prove useful, and we'll know soon. Because we're about to watch this one. So going to cover resonance, but this time, um, again, resonance part three. We first did drawing resonance structures, the rules of how to draw them. Number two, we did the rules of stability and how they impact structure and major minor contributors in a resonant hybrid. This one, we're going to look at how they impact reactivity and or stability. They're kind of opposite sides of the same card. Okay, so I want to start with impact on reactivity. Notice it came in flames because it is a hot topic. It is something that will show up in every single organic chemistry course you will ever take, everyone that's ever been given, everyone that will be given in the future. It's a core topic on organic chemistry tests. Okay, so looking at this compound, I want to identify the functional groups early on just to get in the habit of doing that. But this is what's known as an amide. If it's two amino acids, we call it a peptide linkage. It's non-amino acids, so we call it an amide. So this functional group. And it is imperative to know how amides behave because amides are very common biologically. Hydrogen bonding is a core part of biology. So if I look at this structure, I have this resonance form, and according to my initial thought, my first thought would be going by Funkelbrich. I would predict nitrogen being less electronegative than O would be more willing to share. And so it would be the one most likely to give up its lone pair in resonance. Okay, that's if, or if it hydrogen bonding, excuse me. So lone pair would go into hydrogen bonding. That's if I completely ignore the impact of resonance. So nitrogen is more electron donating than oxygen because it's less electronegative. That's my first thought. This is the power of resonance because there's a minor contributor. Draw this. Lone pairs become pi bonds. Pi bonds become lone pairs. This is repeated over and over and over. So this resonance structure that I would draw, I'm going to draw it down here. Methyl groups stay the same. We now have a single bond to the O, which carries a negative charge caused by the shifting electrons. That carbon is double bonded to nitrogen, which still has an H and a CH3 on it, but now the nitrogen carries a positive charge. So although this is a minor contributor, it fits the octet rule, but you have separation charge, you don't want that. So the major contributor is what we're going to see most of the time, but because of the influence, it's minor contributor because there is just enough of this resonance structure, let's say, I don't know, 90 to 10, just some whatever amount, you put a negative charge on the O and a positive charge on the N, and this Funkelbrich rule that I so loved from previous examples doesn't work. It ends up resonance takes precedence, takes priority over what's going to be known as the inductive effect or electronegativity. Because this O is partly negative, it is actually this O that's lone pair that will go on to form an H bond to N, O, or F, whatever atoms happens to be attached to. So it didn't specify exactly what kind of H it's bonded to. But if you ever look at peptide structure, protein structure, you'll notice things called alpha helices and beta pleated sheets. Those are held together by hydrogen bonding between the peptide backbone. And you'll notice the carbonyl lone pair is donating to an H on an amine or an amide, the nitrogen group of the amide, on another amino acid. So you actually get this scenario. This goes up here to an H, which is covalently bonded to an N, which is linked somewhere else. So that is what you see in biochem. So that O is your lone pair donor in an amide or a peptide. Okay, pretty revolutionary. This, although we've known this for about 60, a little over 60 years, actually, gosh, coming up on 70 years or so, um, the discovery of this was revolutionary in chemistry, both biochemistry and organic chemistry. A lot of people worked on this because it's such a core fundamental concept that you have in bio. So it's actually the O that donates because of the delta minus from the resonance structure. Resonance is powerful. And that's kind of what this example brought up. Okay. It can also, besides predict reactivity, can predict bond length. So which carbonyl is the longest of following in the following compound? So again, this is a question of resonance. You don't recognize it at first, but it is. So I'm going to draw lone pairs on various O's. And I'm going to look at any situation where there's a lone pair next to an atom in a double bond. So these lone pairs, they're on an atom in a double bond, but there's no double bond next to it. These lone pairs are on atoms that are in a double bond, but not next to it. But these lone pairs are on an atom that is on a bond to an atom in a double bond, meaning these are potentially electron donating in nature. So if this lone pair goes in here, that goes up. Again, the same old resonance. Lone pair becomes a pi bond becomes a lone pair. So if I were to draw this other resonance structure, you will see this O now has a positive charge. It is bonded to a carbon. It has an O, which now has an extra lone pair on it and a negative charge. And the rest of the structure stayed intact. So what happens then, these two carbonyls that we're told to compare, this one and this one, this is purely a double bond. Because of resonance, this is mostly double and a little bit single. Okay, so that's where we have to know our information about bond length. If you recall, single bonds are longer than double are longer than triple. So if you have something that's purely double and something that's partly single, mostly double, but partly single, that little bit of extra single bond makes this a little bit longer. So this will be longer. So therefore, by default, be shorter. This one is our reference. We don't do anything with it. This one became longer because of resonance. So resonance can increase or decrease reactivity depending on where you're moving charges. It can also increase or decrease bond length. So if you were trying to analyze this compound and distinguish between these two acetyl bond O's using a technique like spectroscopy, they'll have slightly different values because one is slightly longer and slightly weaker than the other one. Okay, so two things down. We compared reactivity, i.e. hydrogen bonding in one case. We compared bond length. So we'll move on. Which one is the most acidic proton? So Again, my first thought is to consider what the impact of Funkelbrush is. H on an O, H on an O, and H on an N. So I'm going to say these two are my best guesses, um, more so than N, but they're equal as far as I can tell. So when I consider resonance, they each are going to have a resonance structure like this and like this, which means they are equal by resonance so far, but there somehow is this extra impact of this group. It must be doing something. So if I'm trying to compare one group to another, I need to focus on what is dissimilar, not what is similar. So everything in purple is useless to me because it is the same for both this OH and this OH. They're both getting withdrawing from the carbonyl. Okay, so here's what we have to look at. The thing that's different, this nitrogen has a lone pair. Lone pairs we know donate in, electron donating group. If it donates in, I just created an extra bond here. That can't work, so it's going to shift down here. That's going to create a pi bond there, which is too many bonds to that carbon, so this has to come up. So I'm going to get rid of and ignore all my purple and focus just on the blue. So if I focus just on the blue portion, then this resonance structure because this group is donating in to the same spot this one was donating into, this doesn't donate as much. So this O wants electrons, no doubt. So this O up here took it from this OH, this O would take it from this OH, but because there's some electron donation going on here, it doesn't take it as much from this OH, meaning this OH just became less of an electron donor. This one is more of an electron donating group. As a consequence, if this is donating more, this lone pair is being donated more, it's going to make this H a bigger delta plus. If this one is donating less, then this one's going to make this H a smaller delta plus. So larger delta plus equals more acidic. This is where resonance gets really complicated and or intriguing or whatever adjective you want to describe. Initially, the word will be confusing. In time, it'll be cumbersome, and eventually it'll be really inspirationally cool that it actually can solve all problems in the world. Okay, maybe I'm over the top in the last one, but it's a really challenging question. So I'm going to erase everything and go back to the skeleton. So I want to identify the H's I'm concerned with. Those would be these two. They both have identical groups, so I'm going to ignore everything except for this electron donating group. Because this electron donating group, it put electrons here, so it made this one electron richer. Electron richer means less like H plus, because like H plus is about as poor as it gets. Therefore, this triangle of dots means therefore less acidic. So it's by resonance, and hopefully this seems clear. It's a lot of information going on, but this is where we're going with this. So this is how you have to apply this resonance information. So pretty good question, I think. So we'll keep on moving. Oh, so which was most acidic? So which one is most basic? This is a classic bioexample. So let me just put the word up here to begin with. Histidine. It's an amino acid. And if you study anything in bio, you're going to hear the word histidine repeatedly for any enzyme activity. It is basically involved in almost every active site anywhere. It's a very useful compound, and we'll go into more details when we get there. So this is not histidine itself. This is the side chain associated with histidine. It is important, I think, to start off by considering where electrons are being held. Let's start with this pi bond right here. I'll draw that here. And then I'm going to move to this pi bond. That one's covered. This lone pair is in an sp2 hybrid. That's important. This lone pair, because of resonance, doesn't resonate that way, or it could even resonate that way. Does that work out? Not as well. So I'm going to get rid of that one because that put too many bonds to N. So the only one that works is this one going here, and this becoming a lone pair. So because of this minor resonance contributor, we now have a positive on that nitrogen, negative on that nitrogen. But because of that resonance contributor, so by resonance, we can put a negative on here, positive on here. The more negative one is the one that's more basic. So if you recall, OH minus, negative means basic. So I have this electron pair donor here, so that's going to be more basic. And then also I can do it by the other resonance rule, that this lone pair is tied up in a p orbital. So because it can resonate all the way around, this one up here, again, sp2, this one in a p orbital involved in resonance. Because it is involved in resonance, it is not available to be shared. This one is shared. This becomes absolutely paramount in biochemistry to know which nitrogen is the one that's a reactive nitrogen. So in histidine, it is the one that does not initially carry an H. It is your reactive nitrogen in active sites. It's the one that's basic, it can donate in. And once it does that, it can stabilize it because of this resonance stability. So it ends up then that this is unstable. So some professors, some books will tell you, instead of answering this question by deciding which one has a more negative site, they will tell you just go ahead and put an H plus on there and see what happens. So put an H plus here, you lose resonance. Put an H plus here, you still have resonance. So if I were to add an H plus to this structure, so I'm going to draw the so-called conjugate base and conjugate acid pair. So this is the conjugate acid I'm drawing. It will have the structure is such. This is going to have a plus. This has an H and a lone pair. This can be resonance stabilized. Those electrons can move over. So the conjugate acid is more stable. If this gets more stable, it moves in that direction more, which means it's acting like a base more. If this is the H, or this lone pair that picks up the H. A lot going on here. So you can either do the resonance structure and see where the negative ends up. I prefer that method. Or you can protonate it at the two sites and look at which is the more stable resonance structure. It ends up it is this one. Or if you want, you could even look at the orbital theory. Orbital theory says sp2 is available. Lone pair in this p orbital is not available. It's involved in resonance. So you can predict it by structure, which still involves some resonance. You can do it by resonating the lone pair over and seeing where the negative is, or you can protonate both sites and compare which one is a more stable uh, conjugate acid. The more stable conjugate acid is the site of the more basic nitrogen. A lot going on there. This is a really big question. Again, assuming this set of videos is going out to people from all sorts of courses everywhere, I will bet anything, not that you could ever collect and not that it's legal, but if it was a gambling situation, I would bet that your professor will put this structure on here and ask you, where is it protonated? And I would win 90 out of every 100 bets. Just a very, very common question. Okay. Another way of asking which is more acidic is asking about the pK. Another way of asking which is more basic is asking about the pKb. So just a quick reminder, when pH goes down, it gets more acidic. When pKa goes down, it also gets more acidic. So pKs for more acidic compounds are lower, pKs for less acidic compounds are higher. So we're going to consider these three compounds that are called phenols. So you have an aromatic ring of 1, 2, 3, 4, 5, 6 carbons known as benzene with an OH coming off. You have again, benzene with an OH coming off. So you have this thing overall is called phenol. This phenol with an extra little carbonyl or C-O coming off of it. This is a benzene ring with an OH or a phenol with now an OCH3. You should, when it says compare the relative reactivity, acidity, basicity, nucleophilicity, electrophilicity, any way they're asking you these questions, this is acidity. Compare what is different, not what is the same. So in each case, we're looking at this H and trying to decide which is most acidic. So an H on an O is going to beat an H on a C. And then we look at the groups that are added. So this is our reference. They gave this as 10.0. So the question is, how will a pi bond affect this? So pi bonds pull away when it comes to resonance. Meaning this pi bond is going to pull electron density that way, which makes this bond have to shift over, which makes this bond shift over, which ultimately is going to take away electron density. One of the lone pairs is going to come in. So if you do that, so let me go ahead and get rid of that drawing, let the computer generate it. I still want to have a lone pair up here. There are two lone pairs, so one of them is going to come over. If it does that, then electron density is being pulled away. So we're going to say the first atom attached here is part of a pi bond, the first different atom. So H, O, and C. C, part of a pi bond. Pi bonds are electron withdrawing groups. Pi bonds pull away. So if you do that, you make this end electron poor. Electron poor means it is more like H plus. H plus has 0 electrons, about as poor as you can get in electrons. So if it's more like H plus, we've just said it's a stronger acid. A stronger acid will have a lower pK. I have no idea what number to guess, but I will say pK must be less than 10. So if you're guessing number higher than 10, you said it's less acidic. I'm guessing less number lower than 10, it's more acidic. It's still a weak acid, so it can't go down too much. So if you said 8-ish, that's going to be a pretty good guess, about 8.4. So resonance can lower your pK 1 to 2. Okay, so let's go ahead and look at the other group over here. This one, now the lone pairs are actually drawn in for me, which is nice. Lone pairs push in. So lone pairs will push in. So if this pushes in, it forms 5 bonds. That'll break this. That'll push in. This can't push up to O, so it has to put the lone pair here on this carbon. But the point is, it's pushing electron density up and into the system. So therefore, it makes this end electron rich. So when the first atom attached has a lone pair, it's electron donating group because lone pairs push in. Makes this electron rich. Electron rich means it is less like H plus, which means it is a weaker acid. Weaker acids, higher pKa. So this one went down by 1.6. So I'm going to guess maybe it goes up by 1.6, up to 11.6. Ends up only goes to 10.8. The difference being this resonance actually took a lone pair directly off of O. This one puts a lone pair near the O, but not on the O. So it's not quite as impactful. So if you want to go ahead and draw out the resonance structures that have formed, that's not a bad idea. So I will do that here. There's my benzene ring, double bond with an O minus and an H. On this end, you have O, the plus charge. Because the O has a plus charge, it's going to make that group more acidic. The resonance structure that forms from what I've drawn here, same thing, central benzene ring now has L bonds there. It has an O, CH3, with a lone pair and a positive charge. It has a lone pair here and a negative charge next to an OH. So the negative made it electron richer, the positive made it electron poorer. So this structure, not drawn the prettiest you'll ever see, but hopefully those explain what we're looking at. So if you're supposed to draw out the structure that explains it, putting a plus charge on an O, that's going to make it more acidic. That's why the pK went down. Putting a negative charge near the O, that'll make it more basic. But because it's near it, not on it, it's not as impactful. Okay, onward we march. So yet another one. This benzene group is going to be really popular in resonance because there's so many pi bonds, you can move things around. So this is benzene, this is a carboxylic acid, so collectively this is known as benzoic acid. So if we add a CN group, cyano group, how does it affect the pK? So we could add it here, here, or here. I'm going to choose this one just for symmetry of it. So we put it here. The question you have to ask yourself when it comes to these sorts of questions, is there any potential for resonance? And resonance can only happen if you have a pi bond or a lone pair that can get involved. So the group I just added, sure enough, has a carbon with no lone pairs, but it has a pi bond. So pi bonds pull away. Meaning if this bond pulls away, it's going to take it from there, and put a plus charge right here. That plus charge is going to make this one, this group over here. If there's a delta plus, then it's going to make it electron poorer, which makes it more like H plus, which makes it more acidic, which will have following consequences. I'm going to make it go down. Again, resonance should make it go down apparently from before 1.6, so it should go down to 3.4, and lo and behold, it does. So it's anywhere from 1 to 2. It was coincidentally a 1.6 drop in each case, but that is not always the case. But it should go down by resonance by about 1 to 2 in pKa, and should go up 1-ish or so when it's through resonance. We covered a lot of stuff. This was just kind of a little bit overwhelming. These are ones to go back and practice, find examples in your book, get it from whoever your professor is. Make sure you can draw all sorts of resonance structures. So hopefully this helps. I'm going to stop the recording and I will see you at the next Toddcast. Thank you. Bye.